Not. I want you to think about this. You can't push a wagon any faster than you can run. Think about it and hold this in your head. As a matter of fact, what I'd like to suggest for the end, the conclusion I'm going to come to is the wagon has to push itself. Where are we going? Are we going at warp speed? No, we can't be going at warp speed. Warp speed is for Star Trek and Star Wars and science fiction. We are modern scientists, and we know about how fast you can travel. We know how big the universe is. We know all these important things. Or do we? I am able to look at the Milky Way galaxy edge on. Have you ever seen that? The Milky Way galaxy is huge. There's no way we can go there. We're stuck on this little planet called Earth, and we'll always be here or very close to the Earth. It's limiting. Here and there you see dark wisps of clouds created way out in the universe, way out beyond the Milky Way. You might say to yourself, are these important? No. Is this local weather? No. But I have to tell you, it is important. Those are places that we can't go to now. We're limited. I can't have my Star Trek universe. You can't have yours either. Maybe you're totally involved in your head with things that are going on in your daily life and you think this isn't important. I'd like to suggest to you that it is important. It's important for your children. They're cute, they're small, they're growing up, but they are limited. Someday, we may wish that we had the freedom to travel to the next galaxy. I'd like to suggest to you, in fact, I'm quite certain, that where we're going is beyond this galaxy. Star Trek and Star Wars give us a vision of a universe that doesn't limit how far and how fast we can travel. That's my objective. We want that universe. In episode 1, I said the current world model, our cosmology, doesn't support the Star Trek universe. It tells us we're limited in space and time. It started with a bang and will end in silence. Think about whether we need to look at a notion of how the universe is organized that will eliminate that possibility. You have to think about this. Do you want to hear our current cosmology that gives us that limitation? One that ends in that silence? Or would you like to hear about another cosmology? A cosmology that gives us our Star Trek universe. Infinity. Unlimited distance and unlimited power to travel. None of the theories of cosmology that center around the Big Bang Theory have been proved. There's no way to prove that the universe started with a bang. There's no way to prove that the other features that support cosmology based on the Big Bang are true. We chopped down that tree in episode 2. And now what do we have? We have infinity. Here is infinity. I concluded in episode 2 that the universe is infinite, but we have to travel at some speed less than the speed of light. The nearest star system is 4 light years away. That means if we're going at the speed of light, it would take us 4 years. But worse than that, the amount of energy that is currently assumed required to give us that kind of distance is essentially infinite. We can't carry enough fuel tanks to go that far. In this episode, episode 3, I'll show that the limitations of relativity theory are only those limitations of a mindset. This is just what you think. It's not the way the world really is. The world is infinite. I'll give you a new way to look at relativity. Listen. Listen to this and see if it doesn't make sense to you. Fundamental to the special theory of relativity is the notion that this maximum speed. This fact can be proved according to the theory in many ways, but the usual explanation is citing how the linear accelerator operates. You push a particle down a channel using magnets. Magnets require a certain amount of power. And it looks like this. Well, in a linear accelerator, the particles, such as protons, are pushed down this channel. In a linear accelerator, atomic particles, such as a proton, are accelerated down a channel using a series of electromagnets. They can speed us up to very close to the speed of light. But at what cost? At incredible amount of energy cost. Stanford has spent a lot of money providing enough energy to that linear accelerator so that it won't dim the lights in Silicon Valley. Incredible power. The closer the proton gets to C, the more power is required to achieve a fixed incremental increase. For example, think of the power sort of like batteries. How many batteries do I need? If the proton is flying at 1/10 the speed of light, then you want to go faster, you need to add another battery. But 2 batteries won't get you twice as fast. 3 batteries won't get you 3 times as fast. As a matter of fact, it's a process of diminishing returns. And the physicists will agree with you. You can prove this. Obviously, the closer you get to light, the more energy you need. Therefore, you cannot get to the speed of light. You can't push a proton to the speed of light because it would require an infinite number of batteries. So what do we say? This proves that nothing can go faster than the speed of light. We don't have enough energy to even get it close. The problem with this is it flies in the face of Newton's laws of motion. The third law of Newton's laws of motion says for every action, there's a reaction, such as accelerating a proton. Well, this theory of relativity throws that law out. The closer you get to the speed of light, the less of a reaction you get. Does that make sense? Well, it does if you're a proponent of the speed of light. So that speed of light is a hard, fast barrier, and we're quite certain in all of the planning of NASA and everybody else that we should never even consider building a spaceship that can approach that speed. No. That's the limit. Well, there was another limit that we were up against. I know my father's family believed that this was just a foregone conclusion. A plane can't go faster than the speed of sound. In the 30s, going faster than the speed of sound was outrageous. It was just not possible. Well, if you were watching a biplane fly around, boom, 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 they're sort of like a kite, and there's no possibility they could go more than about 200 miles an hour. They started to fall apart. The cloth started falling off the wings. Pilots died trying to speed up their biplanes and triplanes during the First World War. Approaching the Second World War, the speed of warplanes became very important. The aviators kept pushing and pushing to speeds higher and higher, and pilots died again. In the 30s and 40s, aviators struggled with the sound barrier. They just felt there's some way they ought to be able to get through it. no matter how powerful their engines they made, this was one solution to build their engines extremely powerful. Put a big 1,000 horsepower engine on the front of a very light aircraft and see if you could break through the sound barrier. No, it wasn't possible. That sound barrier of about 700 miles an hour became a hard barrier. It took some serious study. They flew, for instance, a P-51 single-engine plane at around 400 miles an hour. That speed required a certain amount of power. If you doubled the power, you didn't get double the speed. If you doubled the power again, you didn't get double the speed. In fact, the closer you got to the speed of sound, the less acceleration you got. Very confusing. They did a lot of study and found out that it was the shape of the plane and the propeller washing around in highly, highly compressed air that prevented the plane from going faster. Eventually, they had to learn to build the plane so that it looked like an arrowhead. Cut through that thick, viscous air, the highly compressed air, and change the wing shape so that the flow around the wings could be controlled so that you could control which way the plane was going to go. That was the solution. About 1947, 48, the Bell X-1 rocket plane was flying and they broke through the speed of sound. It was incredible. It was a great thing. So, if we could break through the speed of sound, is it possible to break through the light barrier? Or does that seem absurd? It's not absurd. To make a breakthrough, we have to grasp light, to understand it. Photons are virtually massless. They're so light, but they can weakly push something. They can push things along. You may have heard about the solar sail. The Americans and the Japanese sent a solar sail up by rocket, and they opened it up, and sure enough, the sun was able to push this. The light from the sun was able to push this. So you could have a spaceship like a sailboat on the Earth, but instead of being pushed by the wind, it's pushed by the pressure of the sunlight. But what's the fastest speed you can go at? The fastest these solar sails can go is something much less than the speed of light. And why? Because light can only push at the speed of light. Light goes, let's say, 186,000 miles a second. I know you'll never get a solar sail that fast, but theoretically, that's the maximum speed because that's the maximum push. The same rule applies, strange as it may seem, on the Earth when we push or pull a wagon. Maybe this is not obvious, but imagine what speed you can achieve pushing a wagon down the road. You ever pushed a brother or a sister or some other friend in a wagon? You might have that personal tactile experience. When the wagon is first starting out, you have to push hard against their weight. Once it gets going, you don't have to push quite as hard. This sounds like something else. If the object being pushed is already going the speed of the pusher, analogous to the sun pushing the solar sail, there's no action, so there's no reaction, there's no acceleration. In this case, if we recall Newton's third law of motion, it doesn't apply in that case. You're not actually applying any force. You can't push a wagon faster than you can run, just as you can't push a solar sail faster than the speed of light. Well, the same is true in a linear accelerator. When pushing a proton down a channel with electromagnetic magnets, they can only push at the speed of light. They can't push any faster because they are essentially using light. The proton, as with a wagon, is traveling as fast as the pusher. The closer you get to the maximum speed of the pusher, light, the less force you can exert on the proton. So that's what the light barrier is. You can't push any faster than light. So how can we do that? What if the proton were able to shine a light out of the back of itself and push itself along instead of relying on the magnets to push it along? It would be independent of the magnets, independent of its environment. In that case, the light speed barrier wouldn't apply because you're coupled. The proton is coupled to the light that it is ejecting. It would just keep pushing and pushing no matter what the speed of the proton. The same applies to any object including a spaceship. If the ship were pushing itself either by conventional chemical means or by light pressure, it would continue to accelerate without limit. The only limit would be, of course, how much fuel you could carry. So, to summarize, the principle of internal propulsion applies to any object using any means to push, propel that object being projected. The means of push can change from, it could be from a mass driver, conventional chemical rocket, or even photonics drive, in other words, using light to push your spaceship. The limitation of speed only depends on the shape of the object and how it interacts with the medium through which it's moving. Obviously, like an airplane, it's limited by how compressible the air is. A rocket in space with sufficient fuel can go at arbitrarily high speeds. What does that mean? Even many times the speed of light. Does that mean we can have our warp drive? The fundamental notion of special relativity, that the maximum speed of anything is not true. Newton's laws of motion uniformly apply when an object is propelling itself with its own internal energy source. It keeps pushing and pushing and pushing. I said I wanted my Star Trek universe, an infinite universe in which we can move about from star system to star system at warp speed, speeds way beyond the speed of light. Now we've got it. And now, if I were Captain Jean-Luc Picard, I would say, engage.